Hi everyone, welcome back. In this lecture we're going to look at the summation operator for generating functions, and we're going to be focused particularly on problems like the following: the sum of consecutive squares, the sum of consecutive cubes, and so on, and trying to come up with closed form representations of those. Let's have a look at an example first. So we're going to let a of x be the generating function for that sequence a0, a1, a2, and so on. What is a of x times 1 over 1 minus x? Well, a of x, we can write it out in full, or at least as many terms as we can in order to start to spot a pattern. 1 over 1 minus x, that's the rational form of the power series 1 plus x squared plus x cubed plus dot dot dot. So the main thing here is what we are multiplying by is the generating function for the sequence of ones. That's really what we're doing here. We're just multiplying by the generating function for the sequence of ones. And we're going to see what happens when we do that. For an arbitrary generating function, when we multiply it by the generating function for the sequence of ones, what happens? Well, let's just work it out. The constant, that would be a0 times 1. So this is a0. What's our linear term going to be? Well, our linear term is going to come from a0 times the linear term in the second polynomial, so that's coefficient 1. So it's a0 times 1 plus a1 times 1. So it's a0 plus a1. And that's the coefficient of x. What about the square term? Well, it'll be a0 times 1 plus a1 times 1 plus a2 times 1. Now we're starting to see the pattern. It's just the sum of the first 3 terms of our original generating function. What about the cubic term? That's just the sum of the first 4 terms. And so on. And so what we see here is that a of x times 1 over 1 minus x is the generating function for the sequence of partial sums. a0, a0 plus a1, a0 plus a1 plus a2, a0 plus a1 plus a2 plus a3, and so on. And it's because of this we call 1 over 1 minus x the summation operator. So because of this, we call 1 over 1 minus x the summation operator. Because what it does is if we have any generating function and I multiply it by 1 over 1 minus x, I get the generating function for the sums of the terms of the sequence, in the sense that it's the first term and then the sum of the first 2 and then the sum of the first 3 and so on. So we can now go ahead and repeatedly do this. So we're going to do a further example. In this case, we're going to start off with our polynomial as our original generating function here. And this is a generating function for the sequence 0, 1, 1, and then zeros for the rest. Okay, so that's our first generating function. Then what we're going to do is multiply it by 1 over 1 minus x. So we get this generating function. And this thing, it's the generating function for the sequence, or in other words, I'll just write generates. What is the sequence it generates? Well, by the previous slide, we know that it's going to generate the sequence. Well, it's going to start with a 0, and then it's going to be the sum of these 2, and then it's going to be the sum of these 3, and then the sum of these 4, and so on. So it generates 0, the sum of the first 2, 0 plus 1, the sum of the first 3, 0 plus 1 plus 1, 0 plus 1 plus 1 plus 0, and so on. And so the sequence is 0, 1, 2, and then 2's from that point onward. Again, because whatever term we are interested in, it's really just the sum of the first number of terms of the original sequence, and that's just the sum of 2 1s and a bunch of zeros. Then we can do it again. So the next question says, okay, let's find a of x over 1 minus x all squared. Well, what is that? That is a of x over 1 minus x times 1 over 1 minus x times the summation operator. So we are applying the summation operator to the previous generating function. So that is this, and what it generates is the sequence, well, 0, and then the sum of the first two, so 0 plus 1, and I'm just going to write down the sum, do the sums in our head rather than write them out, and then the sum of the first 3, 0 plus 1 plus 2, so that's 3, and then the sum of the first 4, 0 plus 1 plus 2 plus 2. So basically we're adding 2 to the previous one. So that would be 5. Then we add another 2, 7, and add another 2, 9, 11, and so on. So that is the generating function for that sequence. And then we do it again. We take that previous generating function and we multiply it by 1 over 1 minus x. And that's going to be x plus x squared over 1 minus x cubed. And what does that generate? Well, that's going to generate this sequence of sums. So it's going to be 0, and then 1, and then 1 plus 3 is 4. So I'm going to write the sums out for this one, just so we can start to perhaps see a pattern. 0, and then 1. I won't include the 0 in the sum. And then 1 plus 3, and then 1 plus 3 plus 5, and then 1 plus 3 plus 5 plus 7, and so on. And so this becomes 0, 1, 4, 9, 16, and so on. And so that looks like the sequence of squares. So we started with, well, at least partway through, we started with 0 followed by the sequence of odd integers, and it looks like we are now getting the sequence of squares. How do we know that this pattern continues? How do we know that we actually do get squares? I mean, the next one is going to be adding 9 to this, which gives us 25, and then we add 11 to that, which gives us 36. So it seems that the pattern's continuing and we're getting squares. But how do we know that really is the case? Well, it's really a question about what is the sum of consecutive odd integers. We know these are all going to be odd because what we're doing is we're just adding on 2 every time. So what we get here is that this suggests moving from this line, applying the summation operator to produce this line. This is suggesting the following result. This suggests that 0 plus 1 plus 3 plus 5 plus ... all the way up to some final odd number, let's say 2n minus 1, is equal to n squared. So that's what this is suggesting. We can check this to see if this is really the case. We can check that we actually will indeed get perfect squares going along down the line here. How are we going to check that? Well, we are interested in this sum, so I'll just write down what this sum is. We are interested in the sum k goes from 1 to n of 2k minus 1. What is this sum equal to? Well, we can split it up. It's the sum, 2 times the sum, k equals 1 to n of k minus, and then we have, you know, what I'm doing here is I'm just summing up the 2k's, and then I can sum up the minus 1, so that would be a, put parentheses there, and then that would be a minus n on the end. What is the sum of k? From k goes from 1 to n. That is just the sum of consecutive integers, n times n plus 1 over 2. And then we're subtracting n from that. The 2's cancel, and we get n squared plus n minus n, or in other words, n squared. And so actually, yeah, indeed, we will get squares all the way down the line here, because what we've just shown here is that the sum of consecutive odd integers produces a perfect square. So this is neat, because what we've actually done here is just through playing with a polynomial which generated a very simple sequence. It was just the sequence 0, 1, 1, and then the rest zeros. By hitting it with the summation operator a few times, we were able to produce the sequence of 0, 1 and a bunch of 2's, which then we hit it again and got all the odd integers, and then we hit it again, got the sum of all the odd integers, which are the perfect squares. So we managed to get a generating function for the sequence of perfect squares. That's quite a beautiful result. Okay, so what we're going to do is we're just going to continue our explorations of this summation operator. But you can also see that we are getting summation formulas in the mix. So the sum of consecutive odd integers, we've got it as a perfect square, which we've argued here. These kinds of things you most likely see when you're exposed to proofs by induction for the first time. So these are often common practice places to do proofs by induction. And because of that, we'll refresh our memories with proof by induction here, and we'll do a few examples of those as well. So we'll explore the summation operator a little more, and we'll also explore or refresh our memories with proof by induction. So here's our main example. We want to find a formula for the sum of consecutive squares. So the sum of consecutive squares. If you think back to this one, we've just produced now a generating function for the sequence of squares. Now we want to produce a formula for the sum of consecutive squares. That means I'm interested in 0, 0 plus 1, 0 plus 1 plus 4, 0 plus 1 plus 4 plus 9, and so on. And so I'm really interested in hitting this generating function again with the summation operator. And so that's what we're going to do. So we know already, this is from the previous slide, that x plus x squared over 1 minus x cubed is the generating function for 0 squared plus 1 squared x plus 2 squared x squared plus 3 squared x cubed plus 4 squared x to the 4th plus dot dot dot. So this is a generating function for the sequence of perfect squares, or consecutive squares. Maybe I should say it that way. Now what we'd like to do is we want to apply the summation operator to this, and then extract the nth coefficient, because that would be the sum of the first n squares. So we take x plus x squared, 1 minus x. Hitting it with the summation operator, just going to bump up the denominator by 1 more. So this is the generating function for the sequence, which we'll say a sub n, which is 0 squared plus 1 squared plus 2 squared plus dot 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 all the way up to n squared. That's the generating function for this. So if we can do a coefficient extraction on the rational form of the generating function, we can come up with a closed form for this sum. So that's our goal. Let's do coefficient extraction on x plus x squared over 1 minus x to the 4th. So we're going to extract the nth coefficient. And to do that, we can just write this as a sum. So it's the sum of x over 1 minus x to the 4th plus, and then the nth coefficient of the other piece, x squared over 1 minus x to the 4th. Now, in order to do the coefficient extraction, we need to use our trusty result. So let's recall that 1 over 1 minus x, in this case it's x to the 4th, that has series expansion, the sum from n equals 0 to infinity, the number of ways to choose n from 4 with repetition. So this is the sum n equals 0 to infinity of n plus 3 choose n, x to the n, or we could write it as the sum of n equals 0 to infinity of n plus 3 choose 3, x to the n. So we're going to recall this because this is our extremely important series expansion of our rational function 1 over 1 minus x to the 4th. Now, having that, we can go ahead and do our coefficient extraction. So what is our coefficient extraction? Well, I'm interested in the coefficient of x to the n of this. But because of that extra factor of x on top, I'm really interested in the coefficient of x to the n minus 1 of 1 over 1 minus x to the 4th. And for the second piece, because of that x squared on top, I'm really interested in the coefficient of x to the n minus 2 of 1 over 1 minus x to the 4th. And so now we can extract both of those using our formula we've recalled above. So this would be n minus 1 plus 3, choose 3, plus n minus 2 plus 3, choose 3. And so this was by the formula above. And so this becomes then n plus 2 choose 3 plus n plus 1 choose 3. So that is what the sum of consecutive squares is. Let's see if we can change the form a little bit. So n plus 2 choose 3, that's n plus 2 times n plus 1 times n divided by 3 factorial, which is 6, plus n plus 1 times n minus 1 divided by 3 factorial, which is 6. I see a common factor of an n plus 1 and an n and also a 6th. So we pull out a 6th, and then we've got n plus 1, which we've pulled out of each term. And then what survives in each term is I've just got an n plus 2 here and an n minus 1 here. So those are the only survivors. And so this becomes an n plus 2 plus n minus 1. And so that becomes a 1/6 n plus 1 to n plus 1. And there we go. That is what an is equal to. And we got that by coefficient extraction on a rational generating function. But that coefficient, if we scroll back up, that is the sum of consecutive squares. And so we've just found a formula for the sum of consecutive squares. So therefore, we have that the sum of k goes from 0 to n of k squared, or in other words 0 squared plus 1 squared plus 2 squared plus all the way up to n squared is equal to 1/6 n plus 1 to n plus 1. And so there we go. We have just generated the formula for the sum of consecutive squares. Now typically when you encounter this probably for the first time, it's through an inductive argument, and you're really just given the formula. You're said, hey, show that the sum of consecutive squares is equal to this result, and then you can prove it by induction. But we didn't do it that way. We generated the formula from scratch. We connected it to generating functions and did a coefficient extraction to find the formula for the nth one. So a very nice technique to see how generating functions can be used to generate formulas for things that we actually already knew. We've been using this one. I think we used it a few times already in this course, this formula. You certainly used it in calculus quite a bit if you've done calculus. But now we see how generating functions can be used to establish the formula to begin with. Let's have a look at the next exercise. So you're asked to use the summation operator to show that the sum of consecutive integers is n times n plus 1 over 2. So this is, instead of doing what we've just done, sum of consecutive squares, you want to now do the sum of consecutive integers. So in order to do that, following the same procedure, you would like to come up with a generating function for which the integers, consecutive integers, are the coefficients, and then hit it with the summation operator, because that will give you a new generating function where each coefficient is the sum of consecutive integers up to that particular value. And then once you've found the rational generating function for that, go ahead and do coefficient extraction. So I'll leave the exercise for you to think about and ponder. I encourage you to work through it and see that you can get this formula using the generating functions approach as opposed to the other ways we've produced this formula. We produced it a few different ways. One was this counting edges in the complete graph. We did it that way, related it to the choice function, and that's where this n plus 1 over 2 can kind of be thought of as a binomial coefficient. If you've done induction, you may have seen this already in Macm 101, proof of this by induction. And so this will have you do it using generating functions as well in the summation operator.